Assalamualaikum warahmatullahi wabarakatuh. My name is Aziz bin Hisham. My matrix number is B132401-500. So basically for this project, our team has been appointed as a junior engineering consultant to evaluate a large-scale industrial refrigeration system at local manufacturing plant in Melaka. So our focus is to identify potential mechanical hazard within the refrigeration cycle, propose suitable engineering solution as safe work procedures, and evaluate the long-term impacts on sustainability, healthy and safety and legal requirements. Through this analysis, we aim to provide recommendations that improve the system safety, efficiency and environmental performance. Now we begin with the overview of our project.
Hello, my name is Ahmad Salim bin Zulkifli and my matrix number is B1324-10569. So our task is identify a specific hazard within a refrigeration cycle. So first of all, I will talk about introduction first. So this have four main components, which is compressor, condenser, expansion valve, and evaporator. For compressor, draws in low pressure, low temperature refrigerant, vapor, and compress it. Condenser reject heat from the high pressure. Expansion valve restrict the flow of the high pressure liquid refrigerant, causing a sudden drop in pressure. The last one, evaporator absorb heat from the refrigerant space or process fluid into the core. The next slide shows four processes on the pH diagram. We have four compressions, condensations, expansions, and evaporation. For compressions, it start from point B to point C. Refrigerant enter compressor as low pressure vapor. The compressor increase its pressure and temperature. The second one is condensations. At point C to point D, the horizontal line at the diagram, the refrigerants release heat to the surrounding. The third one is expansions. From point D to point A, the liquid refrigerants pass through the expansion valve. And the last one is evaporations. From point A to point B, the refrigerant absorbs heat from the cool space. Then the remaining liquid evaporates completely.
Now let's look at phase A. Focusing on the mechanical hazard of compressor failure, we categorize this risk into four areas. First, pressure hazard can cause structure failures, launching flying debris or broken valve fragment. Second, rotating component introduce entanglement risk from unguarded belts, alongside heavy vibration from shaft misalignment. Third, thermal risks include extreme surface temperature that cause burns or worse, or oil ignition leading to flash fires. Finally, fluid kinetic sonic hazard present high decibel noise that damage hearing and dangerous high pressure air injection. Identifying these specification threats allows us to build targeted engineering fix. To address this hazard, our system must strictly comply with both international and local safety standards. Globally, we follow HRE 15, which dictates strict limits refrigerant charge and mandates proper ventilation, dedicated machinery rooms, leak detection, and emergency shutdown system. Locally, for our Malacca plant, we must meet Dodge requirement. This involves frequent pressure vessel inspection, safety refrigerant handling, and mandatory PPE for technicians. Crucially, DOSH requires a comprehensive hierarchy assessment and a clear emergency response plan. Aligning with this regulation ensure our operation remains both safe and legally compliant.
This flowchart shows the safe work procedure for handling refrigerant leak. The process starts with leak detection.
followed by wearing PPE and isolating the system to ensure safety. The refrigerant is then recovered and the leak is repaired. After pressure testing and evacuation, the system is recharged and tested to ensure safe and efficient operation before returning to service.
Assalamualaikum. Now let's move to phase B. In phase B, we will explain the implementation of safe work practice to rectify a refrigerant leak in a refrigerant system. The first step is leak identification. The system is inspected for signs of refrigerant leakage such as abnormal pressure readings, reduced cooling performance, or visible oil stains. A refrigerant leak detector is then used to accurately locate the source of the leak. Next, appropriate personal protective equipment or PPE must be worn before any maintenance work begins. This includes safety goggles, gloves, safety shoes, and protective clothes. These PPE items help protect technician from refrigerant exposure, which may cause frostbite, skin irritation, or respiratory problems. After that, the refrigerant system is isolated by switching off the power supply and closing the relevant valve. This step prevents further refrigerant release and ensures a safe working environment. The next step is refrigerant recovery. A recovery machine is used to remove the remaining refrigerant from the system and transfer it into an approved recovery cylinder. Refrigerant should never be released directly into the atmosphere because it can harm the environment. Once the refrigerant has been removed, the leak can be repaired. This may involve replacing damaged component or performing brazing on the leakage. All repair work must follow the manufacturer's specification and safety requirement. After the repair is complete, a pressure test is conducted using dry nitrogen. This test ensures that the repair section can withstand the required operating pressure and confirms that no leaks remain in the system. The system then undergoes an evacuation process using a vacuum pump. This process removes air, moisture, and non-condensable gas that could reduce system efficiency or cause internal damage. The next step is refrigerant charging. The correct type and quantity of refrigerant are added according to the manufacturer's specification to restore normal system operation. Finally, system commissioning is carried out. The refrigerant system is restarted and operating pressure and temperature are checked. A final leak inspection is performed to ensure that the system operates safely, efficiently, and without any further refrigerant leakage. In summary, following this safe work procedure helps ensure technician safety, protects the environment, and maintains the efficient operation of the refrigeration system.
Moving into phase 3, let's analyze our environmental impact, specifically regarding compressor liquid slugging. Compressors are secretly designed to compress vapor, not liquid. If liquid refrigerant enters the core, it causes explosive pressure such that can shatter valve and ruin mechanical component. To prevent this, we installed a suction line accumulator right upstream of the compressor. This receiver uses gravity to drop dangerous liquid safely to the bottom, while sending only dry, safe vapor through a protective U-tube into the compressor. This simple fix protects the machine from catastrophic failure.
Assalamualaikum and good day everyone. My name is Ni Alif Aiman Hakimi bin Abdulghani. My metric number is P1324101515. I will briefly explain the economic and societal benefit of implementing safe refrigeration practice. For economic benefits, repairing refrigerant leaks and maintaining the system properly can improve energy efficiency, resulting in lower electricity costs. Early fault detection helps prevent major equipment failures and reduce maintenance expense. In addition, a reliable refrigeration system minimizes downtime and improves productivity by ensuring continuous plant operations. For societal benefits, for proper refrigerant handling and leak detection enhance worker safety by reducing the risk of toxic exposure and workplace accidents. Preventing refrigerant leaks also protect public health and the environment by reducing harmful emissions. Furthermore, compliance with safety and environmental regulation improve the company reputation and strengthen public trust. That's all. Thank you.
Okay, next I will present about the sustainability and impact analysis for legal framework in refrigeration safety and sustainability. First, the Environment Quality Act 1974 in Malaysia controls pollution and hazardous refrigerant emission. It ensures refrigerants are handled and disposed properly to prevent environmental damage. Next, the Montreal Protocol is an international agreement that protects the ozone layer by reducing harmful refrigerants such as CFCs and HFCs while promoting eco-friendly alternatives. Legal compliance is important because it improves workplace safety, reduces environmental risks, and supports sustainable industrial practice. For the case studies, industries can use low GWP refrigerants, perform regularly inspection, follow safety guidelines, and maintain proper documentation. So, in conclusion, legal frameworks help the refrigerant industry become safer, more responsible, and more sustainable. Thank you.